For Lab 3, I found the mass of a black hole based on the position data of a star that was orbiting around it. I did this using the momentum principle and the equation for gravitational force. Some initial conditions were that the gravitational force is the only force acting on the star, and that the mass of the star is equal to 1.989 times 10 to the 30th kilograms, that the time step is 86,400 seconds, or 1 day, and that the black hole was at a position of minus 4 times 10 to the 10th meters in the y direction. So to find the mass of the black hole, I started by finding the change in velocity using the data given from the CSV file and the formula delta V equals V final minus V initial over delta T. Then, using the momentum principle, I found the change in momentum per iteration of time. This will be equal to the net force. So to find the components of the change in momentum over change in time, I started by finding that the parallel component of the momentum is given by the line of code shown here. This is possible because the change in momentum describes the speeding up or slowing down of the object, and I found the derivative of the magnitude of the velocity, or this derivative of the speed of the velocity. I then multiplied it by the direction to give this change in momentum. The perpendicular dp dt is calculated by subtracting the total dp dt from the minus the parallel component of the dp dt. After setting some initial conditions, I changed some lines of code in my Python model to find the dp dt, fnet, and their respective components. So as I run the model, the arrows show the respective forces of the net force, the parallel force, and the perpendicular force. These arrows are changing size, which should be expected because the force is not constant, since the black hole is not in the center of the motion. This causes the changes in the magnitude of the arrows. So back to my Python model, after finding this data of the net forces and its components, I decided to find the mass of the black hole using the equation for universal gravitation, and I put that into Python with this line of code. Again, to find the mass of the black hole, I rearranged the equation for the universal gravitation, and I found that the mass is equal to 3.38 times 10 to the 31st kilograms. So to answer some questions, what does it mean? The difference between the net force and the change in momentum over change in time and their parallel and perpendicular components is that the net force causes the momentum to change. Or it is the thing that causes the momentum to change. Since there is a net force applied, the velocity changes and causes everything else, or all the momentum, to change. So what if the mass of the black hole were different, then there would be a noticeable difference. There would be a different net force based on the equation for universal gravitation, and the object would then move at a different rate. So if the data inputted into the Python model is accurate, then the mass of an object can be found based on the observed positions of an object orbiting around it.